Hello, good afternoon, good morning, good evening, wherever you're coming in from. So this is Professor Thomas teaching us anomaly detection. He's taking us on a session in anomaly detection. So this session is supposed to start by 3:30. So we are right on time. I'm seeing people having an issue with the timing. We are right on time. We're just about to start this session. So this session starts by 3:30 and ends by 5. Yes, so Professor is sharing his screen already. I hope we're all ready with our pens and our systems. So let's just give Professor a DSN welcome, even though he's already a part of the DSN community. So hello, Professor, from all around Nigeria, all around Canada, wherever you are, just put your name in the chat box and where you're joining this session from, so we can give Professor, will I say, a chair just to start the lecture. Yes. I know you can't see the chat box now, Professor, but everybody's cheering you on. Thank you so much. I don't think we can hear you. Okay, yes.
Right, I'm just rearranging my screen so I can see the chat box.
Okay, then.
So it's again wonderful to have an opportunity to talk with all of you today and to be a part of this great experience at Data Science Nigeria. So the topic of my last talk is about anomaly detection in machine learning and in computer vision. And And I thought I should start by talking about the various use cases for anomaly detection, because I would say if we think about machine learning over the years, most of the focus has been on prediction, on classification problems, on regression problems, and relatively little attention has been given to anomaly detection. It's often a form of unsupervised learning, or maybe semi-supervised. Um, and so that of course means it's more difficult in some ways than classification and regression. Um, but the first use case, and maybe the most common one, is for data cleaning. So we've already been talking about how when you approach a new problem and you have real data, that often there are errors in the data. Feature values may have been manually entered, and so they have typographical errors. Values in different columns might have been interchanged. Test results from multiple patients might have been combined or intermixed. So you can use anomaly detection to try to detect that these are outliers in the data set that don't follow the patterns of the main data. Another case is fraud detection and cyber attack and things like this. So where we're in a sort of a law enforcement type situation or a defense type situation. And in this case, so obviously data cleaning we do to prepare data for some other task. But for fraud detection and cyber attack, at training or at test time, the thought is that illegal behavior or adversarial behavior creates anomalies in the data, and we hope to detect those. And a third use case that I mentioned is the one of open category detection. So this is the case where at training time, we trained our classifier over some set of possible classes, right, to make classification. For example, in object recognition, we might have trained it on the typical obstacles that we would expect a self-driving car to encounter, or in a medical system, the set of diseases we expect the system to encounter. But the assumption in supervised learning, especially in the case when you're doing discriminative training, so when we train on the conditional probability of the class label given the inputs, which is the standard thing, and we use, say, the cross entropy loss or something like this, we are training the system. We're really telling it that there are only these k possible classes. If you think about the softmax loss, you realize that you are dividing in the denominator by the sum of all the different things in the numerator, which means you are saying that these are the only things that can possibly happen, and that makes the probabilities sum up to 1, which is what we want. But there are many applications in which we might expect to encounter new categories of objects at runtime, and so that might be new diseases in the medical case, new people in a face recognition system, new words in a speech recognition system, new objects in a computer vision system. Then there's the problem of novel subcategory detection. So at test time, we're given a new type of object that is a new kind of category, but is a subcategory of a known one. So we might have, if we had trained a classifier to recognize dogs versus cats or something like this, and we had only trained it on beagles and golden retrievers, when it saw a Chihuahua, it would need to detect that this is a new kind of dog. It's still a dog, but it's a new kind, and it would need to handle that correctly, or a new subtype of a known disease. And the last case is out of distribution detection. So in this case, somehow the distribution of the training data and the distribution of the test data are different. So an example might be a robotic car that was trained in sunny and dry conditions, but then needs to also operate successfully in wet and rainy conditions. So I think these are the main use cases. There are probably others that I haven't thought about, but the point is anomaly detection could be very useful across a wide range of problems. And so the purpose of this talk today, this will be my most technical talk, is to review the different techniques, the different algorithms that we have for anomaly detection, and some of the challenges that we're facing in making successful anomaly detection systems. I should say, actually, the number one challenge is that anomaly detection systems tend to create a fair number of false alarms, right? So when they make a mistake, of course, there are two kinds of mistakes they can make. They can make a missed alarm where there is an anomaly that is treated as if it were not an anomaly. We call it nominal for the cases that are not anomalies. They're the normal cases. But we don't want to use the word normal because it's confusing with the normal distribution or the Gaussian distribution. So, so we'll call it the nominal cases and the anomaly cases, or sometimes I call them the aliens. They're the cases we did not train on. So very often this is a big challenge. For instance, in fraud detection, we'll see that we're going to create fraud alarms, and then some analyst is going to need to look at those and decide whether they really are cyber attacks or not. It's very difficult to take completely automated action based on an anomaly alert, an anomaly alarm. Okay, yes, the slides should be, I sent them in, so you should be able to get access to them soon. I'm not sure if anyone is posting them right now. Well, what is an anomaly formally? We like to say that an anomaly, we define it as a data point that is generated by a process that's different from the process that's generating the nominal points. So these could be sensor failures in the sensor network, fraud, cyber attack, diseases, so on. The challenge is that there is usually very little or no labeled data available. Anomalies are rare, and anomalies may not come from a well-defined probability distribution. So we're accustomed in supervised learning to try to separate the classes that we have with a decision boundary, and that's under the assumption that those data points are coming from well-defined probability distributions and have a boundary. But when you have an adversary that's trying to attack you, every time you make a change, they might make a change, and so the distribution is shifting over time. And there's also a curious problem that I only started to appreciate recently, which is the problem that's so-called nuisance novelty. That there may be things that are unusual about an instance, but they're not relevant for the task or the use case. So if you think about things like website behavior or internet traffic, there could be things that something new happens every day. Say I go visit a website I've never visited before every day of the year, but that doesn't mean that my computer system has been compromised by some attack. Or in images, we might have changes in the background or the context, things like that. So the main strategy that we follow in trying to do anomaly detection is to treat it in some sense as a one class classification problem, where we have our nominals as the one class, or maybe K classes, but they're the nominal classes. And we're trying to detect the anomalies as being outliers, points that are far away from the data in some way. And so a lot of the issue is how do we define a distance that is correct for our task? And if we're using deep learning, how do we define a representation? How do we learn a representation so that the anomalies, when they are mapped into that representation by the lower layers of the network, how do they get mapped into a position that puts them far away from the training data? So are there any questions at this point? Or just on the introduction?
Okay, so you can't unmute yourself. So if you have any questions, please just type them in the chat box so Professor can reply. Okay, I don't think
Okay,
any
well,
questions are there for
right.
now.
I will move on. So there are basically four different approaches to developing algorithms for anomaly detection. And so we'll go through the high level idea here, and then we'll drill down on each of them. So we're going to let D represent our training data. And so these, I will assume that these are vectors in D-dimensional space. So they would be, images or vectors of features or something like this. Obviously, anomaly detection can be extended to time series and graphs and other structures, molecules, and so on. But here, I'll just be assuming that these have been converted into vectors of a fixed length. And so the first set of methods are density estimation methods. And the idea here, actually, let's see if I can get, I do this. Give me my laser pointer here. Yeah, so the first approach are density estimation methods. So we'll try to learn this piece of D, this probability density over the data set D. What is the distribution? We'll build a probabilistic model of our data. And the idea, of course, is that it should assign high probability to points from our training set and low probability to everywhere else. And then we can use what's called, in information theory, the surprise, which is the minus log likelihood of a data point. So given a query xq, a new point, we calculate its probability, p of xq, and then we take its logarithm and negate it. And so why does this give us an anomaly score? Well, if something had probability 1 of occurring, then the log of 1 is 0. And so we would have 0 surprise at all. But of course, if something has a very tiny probability or even probability 0, the log of 0 is negative infinity. And when we negate it, we're infinitely surprised. And so this is the sort of the basic building block in information theory, is this notion of surprise. So this is beautiful in theory, but in practice there are two problems. First of all, if there is something that is a nuisance novelty, some random change in the background of an image or something, then we might assign it a high anomaly score here. So that's a problem. And the other problem is that, as we will see, modeling probability densities in high dimension can take a huge amount of data, can require too much data. So that's the big challenge there. I had another point to make, but I'm missing it. Okay, so right, this is the third point, is that it may be kind of overkill. It might be too much work to build this probability distribution. If we're not really, do we really need all of that? We're mostly interested in just the tails of the probability distribution, where P of D is small, because that's where we're going to assign anomaly scores. So maybe we should instead do what are called quantile methods, where we try to estimate a function f such that when f crosses 0 and goes positive, that defines a region, right? That'll define a decision region in the space, possibly not connected, but a decision region in the space, and that contains, say, 1 minus alpha of the data. So we might create a decision region that contains 95% or 99% of the data. And then we treat everything outside that region as anomalies. And the idea here is that it might be much easier to find this region than it is to estimate the probability density. And this is in fact the case that I'll talk about some quantile methods, whereas non-parametric density estimation requires exponential amounts of data as the dimensionality of the data increases. Quantile methods only require quadratically increasing amounts of data. The techniques that I'll describe are based on kernel methods, so they're related to the support vector machine. And that means they require some kind of a distance metric and choice of kernel hyperparameters. And this means they are still vulnerable to irrelevant features, to nuisance novelty. Even simpler than those first two is the most basic method, distance-based methods. And we just ask, given a data point xq, what is the distance to its nearest neighbor? We'll just calculate, or maybe to its k nearest neighbors. And the farther away the data point is from its nearest neighbors, the more likely it is to be an outlier. That's almost the definition of outlier. And so this requires a good distance metric, which will be a challenge for us in deep learning. But and it still could be vulnerable to irrelevant dimensions. And then the final approach are projection methods. And the idea here is that we take our data and project it down into a lower dimensional space. And in that lower dimensional space, we apply one of these strategies, typically density estimation. But we can do that many times, like say 1,000 different random projections. And each random projection, if we make it sparse, that is, it's a low dimensional projection, then that only involves a subset of the features describing XQ, then that means any one view of the data only is using any one sparse projection of the data is only looking at a small subset of the whole vector, and so that makes it more robust to irrelevant features, to nuisance novelty. And then we get anomaly scores from each of those projections and average them to get an overall anomaly score. Okay, so the body of the talk now is going to be about density estimation, because this is the area that has the longest history and the most methods. So we'll see. First, I'll talk about parametric models where we fit basic probability distributions, mixture models, kernel density estimation, and then some more recent advanced methods. So what is density estimation? Well, assume we're given a data set of big N points, so x1 up to xn, where each of these xi as a member is a d-dimensional vector of real values. We're going to assume the data have been drawn independently and identically from some unknown probability density. And our goal is then to estimate P. The requirements, of course, is that P should be non-zero everywhere, and that if we integrate it over all of RD, it should integrate to 1. So that's the sort of syntactic definition of a probability density. So suppose that I have computed a density estimator P hat for P. How can I tell whether it's any good? What's the equivalent of checking on a validation set? Well, a good density estimator should assign high probability density to places where P is large and low density to places where P is low. So the standard metric we use is the log likelihood of a separate test or validation data set. So we just take the log of the probabilities and add them up, and this would be our objective, to maximize this on the training data and then to check on the separate test data if it is large. So we can still use maximum likelihood, which is the standard way of training all statistical models. But it is, of course, important that we use a holdout likelihood. So it's the same as with supervised learning. We always want to evaluate on independent data that was not used to construct the density estimator. So given our data, we can split it into a training set and a test set. We estimate P hat on the training set, and then we evaluate it on a separate test set. Just a few reminders. I'm assuming you have seen probability, introductory probability before. And so you know that a density, the difference between a density and a probability. So density is a continuous function over the input space that is non-negative, but can be larger than 1. It's actually strictly known as a measure, because it assigns for any measurable subset of the input space, it assigns a probability to it. And you get that probability. An event is a subspace of the input space, and the probability of an event is determined by integrating over that subspace. So we sum over all the elements in E the measure mu of x. Examples, the most famous example is the Gaussian or normal distribution, right? And it has this famous formula, which when you strip it all away is basically calculating the Euclidean distance between x and the mean of the distribution, scaling that by the standard deviation, and then squaring it, and then negatively exponentiating it, so that as that distance gets large, the probability density drops and heads to 0 exponentially fast. And then it has this term out in front to make sure that this thing integrates to 1. But we can also look at the cumulative distribution function, the CDF, right? And that's the CDF evaluated at value z, given mu and sigma, is the probability of the event that this subset from -infinity up to z. So from -infinity up to, say, z minus 2 is this value here, which would be this probability. I don't know what that is, 0.02 or something. And so we get it by integrating the density from whoops, that should be -infinity up to z. Okay, so if we need to, suppose I'm given my vectors, and I actually want to estimate a probability density. This definition of the normal density is for one dimension, but there's the multi-dimensional version of the Gaussian or distribution, in which we have, instead of sigma, we have the covariance matrix, capital sigma, and we calculate the matrix inverse of it. And so this is called a quadratic form here, right? We take the difference between x and mu, and then take its transpose and multiply it by a sigma inverse, and then multiply that by x minus mu again. That gets us a scalar value, and then everything else is basically the same. The normalizer gets a little different. And we can fit this using what's called the method of moments, right? We can calculate the mean just by taking the average of the data points, and we can calculate the covariance matrix, sigma, by taking the outer product, that is x times x transpose, in this case, x minus mu times x minus mu transpose, and adding those up to get the covariance matrix. So it's fairly straightforward. Okay, so as an example, I sampled 100 points from a multivariate Gaussian whose mean was 2, 2, and whose variance was this covariance matrix here. So it has a variance of 4 in the vertical axis and a variance of 2 or a variance of 1 in this axis, right? And but there is off diagonal terms which cause this distribution to be tilted relative to the coordinate system. And then if you estimate the mean and the variance and the covariance from this data, you'll get estimates that are not quite right, right? So instead of 2, 2, we have a little bit of underestimation, but this is pretty close. So that's the basic thing. Okay, so if we now let's think about how we could do better, because most data are not Gaussian distributed, right? So we need to have a more flexible probabilistic model than just a Gaussian. So a very important idea in the history of probability is the idea of a mixture model. So we want to suppose that our data consist of clusters of data points, but each cluster is a Gaussian. Then we can write the probability of x as the sum over the clusters of the probability that the point comes from cluster C times the probability distribution of x, assuming it comes from C, so x given C. And if we write that down as a graphical model, we have this discrete variable C that indexes the clusters, and then this observed variable x that is the actual values that are generated. So these are called the mixture components. These clusters are called components, and each component has its own conditional probability density, P of x given C, where C is the component. So just as an example, here I created a mixture of 2 Gaussians, this one that looks like this and this one that looks like this. This one, this component has probability 2/3, and this component has probability 1/3. And so the circles come from the first component and the pluses from the second component. Now, a key thing to notice here is that these overlap. So there is this region where points could have come from one component or from another. It's a mixture of the data here. I mean, mathematically speaking, every place here has a non-zero probability of being generated by this or by this Gaussian, right? Because the Gaussian has non-zero support everywhere in the real line. But when we look at the cluster of points, we can see we even have some circles way out here that come from this distribution, and some pluses, of course, out here. So if we didn't know which points were circles and which points were pluses, how could we estimate them? Well, that's the idea of fitting a mixture model. And there's a lovely algorithm called the expectation maximization, or EM algorithm, for fitting them. You have to choose the number of cluster components K, and then we're going to create a matrix R of dimension K by N, where N is the number of data points. And this will represent this quantity, which is the, I call it the membership probability or the responsibility. So for a point Xi, what's the probability that it came from cluster K? So if we come back here and consider one of these points here, the probability that it came from this cluster versus this cluster is probably about 50-50, right, for these points. And so those would be, but for a point that's over here, it's probably more likely it'll have a higher responsibility of having come from this cluster than from this one. So what we can do is randomly initialize these responsibilities, responsibility of cluster K for generating point I, subject to the constraint that they sum up to 1. So we might use the uniform distribution, but actually it's good to randomize it, as long as we don't assign zeros to anybody. And then in the main loop, we alternate between two steps, the M step and the E step. In the M step, we assume that the responsibilities are correct, and we estimate the model parameters. And we do this by using these R values. So the mixing proportions, the probability that that the point was of the points coming from cluster K, we do that by just summing up the responsibility of cluster K for all the points. And for the mean, we use the responsibilities as weights and take the weighted sum of the XIs for cluster K. And then for the covariance, we take the weighted outer product of the points for cluster K. Okay, so this will fit, we will fit K different Gaussian distributions with K different means and K different covariances, and then the so-called mixing proportions, which is, you know, in my example back here, 2/3 and 1/3. Okay, so now that's the M step. In the E step, we recompute the responsibilities. So we say, well, what's the responsibility of cluster K? It will be the fraction of points that belong to cluster K times the probability density that point was generated by cluster K. And then we sum up and normalize these to get our new responsibilities. And so if we alternate between these two steps, they gradually come to fit the data. And here's an animation showing what the EM algorithm does as it runs. So it starts with two Gaussians that were very close to each other and kind of in the middle of the data, right? They're very far from the data, those two little pancakes. And then through the iterations, the two cluster components find the data and focus on it. So the EM algorithm, this is on a data set for a geyser at Yellowstone National Park called Old Faithful, about the duration of its eruptions and the delay in those eruptions. And it turns out to exhibit a mixture model behavior. So one warning about the EM algorithm is that it is a form of local search. It's actually a variational technique, but it's doing a local update. And so if you reinitialize it and run it again, you might get different answers each time you run it. And so it is a good idea to run it multiple times, or to create an ensemble of Gaussian mixture models and use them. So here are the results. If I run this in the R language, there's something called the mclust package, which will do mixture model clustering, and we end up with these estimates from our mixing proportions. It's not 2/3, 1/3, but it's close, and the means were not exactly the true values, but in particular we we got the mean of the pluses. It's too small in the x1 direction by quite a bit. So you can see that it doesn't necessarily find exactly the right answer. But these contour points show you that it's fit the distribution pretty well. So we could use this for anomaly scoring, and it would work fairly well. Okay, so the summary for mixture models is you can fit very complex distributions. But EM is a local search algorithm. A main issue is, well, how do you choose the number of mixture components? And so this is a hyperparameter that you need to try multiple values. In our work on anomaly detection, what we did was just build an ensemble. So we fit mixtures with 1, 2, 3, 4, and 5 different components for our data. And then just use the average surprise averaged over all of the individual models to get an overall anomaly score. There is also a failure mode. If a cluster zooms in on a single data point, then the covariance matrix will, the covariance will go to 0, and it'll assign infinite probability to that point, which means you'll get a floating point underflow or divide by 0 error in the code. So a typical thing to do is to add a penalty function that prevents the covariance from ever going to 0. So you can use use a Bayesian approach where you put a prior on the covariances that pulls them away from 0. Okay, well, the third density estimation technique that I wanted to talk about is kernel density estimation. And this is sort of, we went from having a single Gaussian describing all the data to having, in our case, 2 Gaussians that describe the data. Now we're going to put a little Gaussian bump on every single data point. So it's the limit of a mixture model where we have 1 mixture component for every data point. And so the probability density is going to be estimated using, we call it a kernel function, but it could be, and often is, a Gaussian, where we take the distance of x from the xi from, no, let's see, we have, here are our data points, xi, I equals 1 to n. So now given a new point, x, really xq it should have been, we compute its distance to every one of the data points, and then pass it through a kernel function that has a variance of sigma squared. So the kernel function would look like this, right? Where it takes as input, I should have called this something else instead of x, but it takes this distance as input, and runs it through a Gaussian. And the sigma squared is the bandwidth or scale of the kernels. So here's a picture. If I had a set of data points here, these 6 data points, I can imagine putting down a little red Gaussian bump that's centered on each data point and has some variance to it. And then I just add all those up, assigning them each a weight of 1/6. In this case, there are 6 points, because each of these bumps itself integrates to 1. So if I multiply them by 1/6, then this is the sum of all of them is my kernel density estimated. Okay, so what is a data point and how can it be gotten? In our case, a data point would be, it could be a record of a customer at a company. It could be, it's a training example or a test example, right? A d-dimensional example. In this case, I just have 1-dimensional data. So, so this is how we can fit a very sort of arbitrarily complicated probability density, and with that without assuming that it's a mixture of Gaussian components. Even though we're using a little Gaussian kernel here, the exact shape of the kernel doesn't matter very much. It really affects just the tails out here at the end. And so it's quite robust to the choice of the kernel. We do have a design decision about the bandwidth. If we use a bandwidth that is too narrow, then we get a very bumpy fit where there's a bump on every data point. A good choice maybe gives us something like this. And if we go overly smooth, we end up with just one, something that looks a lot more like a Gaussian, a single Gaussian for the whole data. So you often can use cross-validation or a separate validation set to choose the kernel width. So that's this sigma squared parameter here. So so kernel density estimation is a beautiful thing. Unfortunately, in high dimension, and in machine learning, we're almost always in high dimension. High here means like more than 5. So let's say it suffers from the curse of dimensionality. The amount of data required to achieve a desired level of accuracy scales exponentially with the dimension of the problem, according to e to the d plus 4 over 2. So basically, this completely fails in high dimension. So, so those are the standard density estimation things that you might see in a typical introductory course on density estimation. Now we get into the wild and crazy stuff. So a very interesting idea is called noise-contrastive estimation. And it's kind of hard to track down the history of this. In the Hasty, Tibshron, and Friedman textbook from 2016, Elements of Statistical Learning, the second edition, they say it's well-known statistical folklore. So I guess this is stuff that was discussed in the hallways and over coffee among statisticians. But there was a paper in the machine learning literature in 2010 that introduced it by Hagarinen, right, who's a very important machine learning researcher in Finland, and some colleagues, in which they describe these as unnormalized statistical models. So that's only 10 years old. So this is relatively recent. Although maybe it's been in the hallways of statistics departments for decades, who knows. The idea is we have our data set D, and we're going to, so the main idea is we're going to convert this problem into a supervised learning problem, for which we have all of our beautiful supervised learning tools. So the idea is we're going to label all the points in D as belonging to class 0, and then we're going to synthesize class 1 points by uniformly sampling points from our space. Basically, we have to define a box around the data, or a region around the data, but usually we just use a hyperbox. So just look at the, not just the maximum and min along each dimension, but a box that contains the data and extends outward from it a bit. And then uniformly randomly sample points from that, usually a same number of points as we have in our data set, so that we have a well-balanced supervised learning problem. And then fit a classifier to it, we want a flexible classifier. So I wouldn't use a linear classifier, I would use something flexible like a deep neural network, or I like boosted regression trees for this purpose. And then we can just use the value of this fitted function as our anomaly score, because it's been designed to have high values on these random points and low values on the known data. So this is a dead simple idea, super simple idea. We can make it a little bit, so let's look at a picture of it. Again, here's a set of data points that I drew, simulated data in 2 dimensions. So we have two features. I'm calling them X and Y, which is probably unfortunate, but and then I add a random sample. So I define a box that goes from -6 to +6 around the data, right? I had already plotted that. So there's some room around the data points. And then I uniformly randomly sample these pluses from this entire space. Now I fit my function, and then if I threshold it at 0.5, the red circles are circling all the points that have been declared to be anomalies using 0.5 as a threshold. Okay, so that's a kind of arbitrary choice, but we can see that there are pluses all through here, of course, because we did uniform random sampling, but it's treating those. It's not confused by those. So it correctly classifies all these circles as being not anomalies. It does hear some false alarms, this circle and these circles here, and I think there's some more down here that are false alarms. And here's one too. So, but it's doing quite a good job. So this is the Yeah, I see this comment by Ndu Jude, who's, and I'm probably absolutely destroying these names. Data points are like clusters you have around each point, and it's generated automatically when you fit the algorithm. Yes, so that's from the point of view of kernel density estimation, is we're sort of treating each data point as like a miniature cluster. Yeah. Okay, so in noise contrastive learning, this works well in low dimension. The big challenge is in high dimension, these uniform points, it's hard to fill the entire space. But people have gotten some good results. The fitted function that I use, I like GBM, which is the gradient boosting machine. It's available in both R and Python. There's also the package XGBoost, which is a similar but scales even better to larger data sets that you can use for this purpose. So you can set up GBM to do a logistic regression, that is to use what's called the logit link function. And so what it's doing is it's modeling the log of the odds, the probability that the data point belongs to class 1 versus class 0, as a linear sum of decision trees, in this case, trees or regression trees. I think they're decision trees. And so, but each of these trees is very shallow. I used a depth of 4. And then it learns the trees F1, F2, F3, and so on through a boosting process. And I use the number of, the so-called out-of-bag method to choose the number of trees. It chooses 325 trees in this case. So GBM is very flexible and I think works very well. You know, many people have won Kaggle competitions using GBM type methods with few, as long as we're in not too large. So this doesn't work for images, but it would work for modest dimension problems. And maybe I'll skip this, but you can actually derive mathematically that the anomaly score is actually the negative log of the probability distribution, is basically this weighted sum. So it's actually makes sense from a probability distribution standpoint. The idea is that our class 1 data points, because we drew them from the uniform distribution, we know that distribution. So we can basically solve for the class 0 distribution, which is our data distribution. So this is a density estimation method. So there was a really nice paper at ICML this summer using this technique. It came from John Sipple at Google. And so I didn't have access to his slides, but he does have a video from his poster presentation. So these are screenshots from the video. So they're a little blurry and I can't really magnify them. But Sipple is in charge of managing the buildings that Google has. They have 145 buildings. And these have many climate control devices installed on them, right? 15,000 climate control devices. So they're making 120 million measurements every day. And what he wants to do is look for anomalous readings of these measurements that might indicate that something is either that a component is broken or a setting is wrong in the configuration or something is happening. So this system is now live at Google. It's been running for more than a year, and it's been used to create 458 technician work orders with a 44% true positive rate. So that means, as I say, you always have false alarms when you're dealing with anomaly detection, but 44% is pretty good. So he has implemented this dashboard, and again, you can't see it very well, but these are the anomaly scores that are being computed by his anomaly detector, and he uses this noise contrastive technique. And when he gets a high anomaly score, he generates an explanation. So this is if you drill down on one of those, you get an explanation that says that you know, this anomaly score it's actually, this is not a very anomalous score here, but can be attributed to these different sensors with these probabilities. And he also gives a visualization in terms of the typical range of these things. So the idea is that you have a sort of building manager who's looking at this display, and when they get an anomaly reading, then they drill down to judge whether they think it's really a problem or not. And if it is, then they create a work order, a trouble ticket, and send a technician to fix it. And so what he does, I can't remember, I think his data for, is he doesn't do all 15,000 devices at once, but buildings are broken down into zones and that are called cohorts. And so there's separate anomaly detection within each zone of each building. So I think his typical dimensionality was in the 30 to 60 range. And so he uses this noise contrastive technique to find, to train the anomaly detector. Okay, well, the last density estimation technique that I want to describe to you is called flow models. And these are the, I'd say, least mature. These have been developed in the deep learning field just in the last few years. And so I'm sure that the first time you see this, it's hard to understand it fully. So you'll need to come back and review the slides and dig into some of the papers. People have code available and GitHub that implement these, so you can experiment with them. So the basic idea is, suppose we have these d-dimensional data, which are training, each training example X is a d-dimensional vector, and we want to model the joint probability distribution, P of X. Now, it turns out there is a chain rule of probability that's a bit like the chain rule of calculus, that we can write the joint distribution over d dimensions as a product of individual conditional distributions. So we can say we can model the probability of just x1, the first dimension, and then the probability of x2, given that we know the value of x1, and then x3, given that we know the values of x1 and x2, and so on. And if you had all of these probability models, then you could, given a new input x, you could plug in all of these values, estimate each of these densities, or compute each of these densities, multiply them together, and you would get the probability density for the whole distribution. So this, we factor the distribution into these densities. Now, we're going to, these are sometimes called autoregressive because each step is a each of these models is a regression model that predicts, say, feature X3, given the values of X1 and X2. And so if this were a time series, it would be called an autoregressive time series. So we can start by modeling X1 using any of the techniques we described, for instance, a kernel density estimator or a Gaussian. And then each of these, we're going to fit a regression model, possibly linear or not. So linear regression turns out we can view it as conditional density estimation, estimating these are all conditional densities, right? Because they're conditioned on some variables. So if we were doing standard least squares regression, that models the probability of y given x as a normal distribution with a mean that varies depending on x, because the mean is computed as a linear function of the x's, right? Where these beta naught and beta 1 are the learned weights that define the mean function, and the variance is assumed to be a constant that's fitted to the data. So we could do neural network regression, where we can model the mean as a neural network with some weight vectors, and we can estimate the variance, for instance, then as just the squared error of our fit to the observed y values. And so there are a bunch of different methods that have been developed. I'm going to describe something called masked autoregressive flow, which is from Papamakarios and colleagues from the Netherlands. They're going to implement each of these they're going to implement each of these conditional probability distributions as a Gaussian distribution, where the mean is a neural network function of the values x1 up to xj minus 1. And the variance is actually a standard deviation function, is also a neural network fitted to the data. They're representing the variance as the exponentiated value of alpha j. Alpha j is therefore a real value that can be negative. When we exponentiate it, we get a positive value, and that is the standard deviation. We square it to get the variance. It's been known for a long time that if you want to sample from a Gaussian distribution or any complex distribution, you can always start by sampling from a standard normal distribution and then transform that sample. In particular, if you sample uj from a normal distribution and then multiply it by the standard deviation, yes, okay, and then add in and then offset it by the mean, you get a sample from this distribution, right? But it turns out this is known as a reparameterization trick. It has the advantage when you do this that first of all, if you want to sample, you can easily sample from these standard normals. But the other advantage is that we're going to be getting a loss, and we want to back propagate it through this complex normal distribution. We can back propagate it through this simple linear function. So it makes it easy to implement in DeepNet. So there's another way that you can look at what's happening. If we've built this huge, this big chain of conditional models, and each one of them has been parameterized this way using this reparameterization in terms of a standard normal, then we can view this as taking a d-dimensional standard normal, this a random d-dimensional standard Gaussian vector of values from this known probability distribution, and then transforming those values into an observed x value by some function. And this function is this whole collection of neural networks that we're constructing. So the question is, we know P of U because it's from a known distribution. Can we compute P of X, which is the thing we want? Well, we can do it if F is invertible, then we could take F inverse of X, and that would give us back this U value, and then we could calculate its density according to the standard normal density. This almost works, except that F might actually damage the property that a probability density needs to sum to 1, or integrate to 1. But it turns out there's a simple fix for that. If you can calculate the Jacobian matrix, which is the collection of all the partial derivatives of F inverse with respect to each of the, for every J prime pair of features, you form that matrix, calculate its determinant, take its absolute value, and multiply this probability by this value, then you get something that is guaranteed to integrate to 1. So this is a well-known change of variables formula in probability theory. So it turns out that in masked autoregressive flow, we're going to exploit this triangular structure. So if you think about this thing here, we're creating a sort of triangular dependency. The dth value depends on all of the previous variables, but when we're in here, each variable only depends on the variables that have indexes lower than it. So it's sort of I think of it as a triangle in the space, and it turns out that that the derivative is simple because of the triangle structure of the chain rule, and the determinant also is of this turns out to have a very simple form as well, and that's why a lot of these design decisions were made. And the F function turns out to be very easy to invert as well. And so you end up with what's called the masked autoregressive flow. You can think of, if you imagine this is a neural network that would depend, where everything would depend on everything else in the standard fully connected scheme, we're going to mask that out so that this variable on the output is only allowed to depend on things from that we're going to index the input features 1 up to D down here. And so then the outputs are going to go from 1 to D also, and this the jth output can only depend on 1 up to J minus 1 as a sort of triangular dependency. And so you can think of this as putting a mask over the weights of a neural network and only allowing the weights to turn on if they're inside the mask when you're doing the calculation. And so then as we calculate, say, different values, the mask, if we're calculating the very last one, it can look at all of the inputs in making its computation. So it turns out that one masked autoregressive flow network is often not sufficient to model a good probability distribution. So here was a true probability density, and this was the density that was fitted by a single masked autoregressive flow network. And this is the distribution of the U values that were fitted. And the U values are supposed to come from a multivariate Gaussian distribution. And so we can see here, this is very much not a Gaussian distribution. So what you can do is you can take these U values and say, okay, let's model this distribution by another masked autoregressive flow. And if you do that 5 times, you end up with this fit. Here is the true density, here's the fitted density, and this is what the deepest U values look like. And now they look like a nice Gaussian cloud of points. And so that's how you can decide how many of these math modules to stack in order to get a good fit. So this is a very intriguing idea. Unfortunately, people have found that it has a couple of drawbacks. One is that because the U distribution is a Gaussian distribution, it has Gaussian tails. That is, they decrease exponentially fast. And it turns out that these transformations retain that property. So if these distributions, if the true distribution has heavier tails, like it has T tails or Pareto tails, there's lots of natural data that looks more like power law data and has a lot of fatter tails. This method won't fit well to it. But it was discovered last year, this paper here, showed that if you, instead of using a multivariate Gaussian, use a multivariate student T distribution, then you can generate distributions with heavy tails, which the Gaussians can't do. And this was a test at likelihood from their paper where they showed that these maths were working quite well, although they also used mixtures of Gaussians in some cases to fit the data. Okay, so that's the end of all of the density estimation methods, and that took an hour. So that was the body of the talk. Now I will spend less time talking about some of the other techniques. There's this famous saying, I guess, from Vladimir Vapnik, that you should never solve a more difficult problem on the way to trying to solve your actual application problem. And so many people have argued that all this fancy density estimation stuff is solving a more complex problem than we really need to solve. Maybe we just need to find a decision boundary that contains the data and then treat everything that's outside that boundary as an anomaly and raise alarms for it. And so that's the idea of the one-class support vector machine, is to find a function f that contains 1 minus epsilon of the training data. And there's a similar method called support vector data description. F finds a hyperplane or a sphere in support vector data description. It finds a sphere in what's called the kernel space. And we don't have time to talk about that, but basically it's very closely related to kernel density estimation. But instead of putting a Gaussian kernel on every data point, we choose a subset of the data points that are called the support vectors. and we just calculate the distance to them, and that's what goes in the kernel here. And then we take a non-uniform weighted sum, so we also learn weights on these kernels. And then there's a sort of intercept term that we subtract off, and this gives us our function f. So fitting these methods, you have some hyperparameters that you have to choose. You have to choose your kernel. We almost always use a Gaussian kernel for these methods. You have to choose the kernel width, and you have to choose this parameter rho. The third approach to anomaly detection are the distance-based methods, and I mentioned them earlier. And maybe we don't even need to estimate probability densities. Maybe it's sufficient to just, given a query point, measure the distance to its 3 nearest neighbors and take their average, or in this case, the distance to these 3 nearest neighbors here, and use this. We then just need to choose a threshold on that distance to decide what's a big enough distance to have an alarm. Of course, this does require having a well-defined distance, and there are some more sophisticated versions of it. There's an algorithm called local outlier factor that normalizes these distances by looking at the distances of each of its nearest neighbors to their nearest neighbors. Because if you're in a sparse part of the space, maybe a long distance might be a normal thing, whereas if you're in a very dense part of the space, maybe you should expect smaller distances. So that's a normalization of the nearest neighbor method. So how can we compute distances? Well, one method in high dimensional data, a standard Euclidean distance might not be relevant, right? Some features might have come in different units. And of course, one thing we could do is just try to scale them, scale all the features to have 0 mean and unit standard deviation. And that's the classic thing. But it's often wise first to apply principal component analysis and rotate the coordinate, which basically can rotate the coordinate system so that the coordinate system is aligned with the directions of maximum variance of your data. So, here's a case of 3-dimensional data and projected down onto its first and second eigenvectors by principal component analysis. And that spheres the data, makes it now distances are going to be more sensible, right? And so an alternative is to fit a multivariate Gaussian distribution to your data. Actually, principal component analysis can be viewed as doing this. But instead of doing PCA, you can just fit a multivariate Gaussian and then use what's called the Mahalanobis distance, which basically is taking the squared Euclidean distance, but scaling it by the variances, basically the eigenvalues of this distribution. Method 3 is you could fit a random forest classifier and use the same random forest similarity distance. So it turns out if you've played with random forests, you know that one of the other things you can get from a random forest classifier is a similarity score. That is based on looking at the empirical probability that the 2 different data points, x and x prime, get sent to the same leaf in a randomly selected tree within the forest. So it's the probability of 2 points ending up in the same leaf across all of the trees in the forest. And I like this method because it can work with discrete data as well as continuous data, and also it can deal with higher order interactions. Gaussian approaches can only look at pairwise interactions. But you have to remember that any of these transformations that you do on your data are part of the training process and should be computed on the training data only, and then applied to the validation and test data. Okay, and then the final approach that I want to describe are these projection methods, the isolation forest and LODA. So the isolation forest is actually my favorite anomaly detection algorithm, and we implemented it at BigML as our standard method. And some of the other big vendors are also using it. So the idea is to build random binary trees and build a forest of them. So we choose some attribute, J, at random from our data, and then we split. Then we choose a splitting threshold theta, uniformly at random between the minimum and maximum values of the attribute j among our data here. And then we do that recursively until every data point is in its own leaf. I see there's another request for the slides. The slides are available on Google Drive. Okay, there it is. Yeah. So every data point is we're growing this tree in some sense way too deep. If you use standard decision tree algorithms, you would never grow the tree all the way until there was only one data point in each leaf. But our goal here is to isolate the data point, and the quantity we're interested in is how many of these random splits did it take to get this data point to be in its own leaf, and we'll call that d of x the isolation depth. And the intuition is, if a data point is an outlier, then doing these random splits on the data set, it should take very few random splits to separate the data point from all the other data, right? Whereas if a data point is deeply buried inside a dense cloud of points, you're going to have to split on every possible feature, possibly multiple times, to isolate that data point from the rest of the data. And of course, the tree structure as a data structure is very efficient because it's only a log depth in general. And so it takes only a log amount of time to evaluate this distance. And we can grow one tree using all of the data. And it turns out that with a forest of trees, we're getting a good approximation of a distance, an L1 distance between this point and the other and the data. So they repeat this capital L times. So we'll have, say, 100 or 500 or 1,000 of these trees in our forest. And we'll let d bar be the average isolation depth of this data point. Then they have a way of normalizing that by calculating theoretically the expected depth if the data points were just fully random. And this gives them an anomaly score, where normal points should have an anomaly score of 0.5. And then as you get above 0.5, you're going to get stronger and stronger anomalies. Okay, the other interesting method that's relatively recent is called LODA, the Lightweight Online Detector of Anomalies. And this is by Pevney and was published in 2016. And the idea here is to create a set of L sparse random projections. Now, what it means to be sparse is that you choose, say, 3 features at random, and then assign actually normally distributed weights to those 3 features, multiply the weights times the features, and that gives you a single real value. Take the dot product between the weight vector and an instance, and that gives you a single real value, and then you build a one-dimensional histogram or one-dimensional density estimator of that projected value. So we're going to fit a capital L one-dimensional density estimators, each one fit to a different projection. So for instance, if we projected just onto the x-axis and then fit a kernel density estimator, we would get something that looks like this. If we fit along a 45-degree line, we get this density estimator. And if we think about this data point here, it's assigned reasonably high density in this projection, but very low density in this projection. And so again, we can take the average surprise over all of these estimates, and that gives us our anomaly score. It should be an A of X, but that's our anomaly score. So my student, Andrew Emmett, did a large benchmarking study to try to compare all of these different anomaly detection algorithms, because it was our observation that the research community was not doing a very good job on benchmarking. And so you can get his earlier version of his work from arXiv. His master's thesis should be available soon from Oregon State University. It may already be online at the OSU library. But here was our benchmarking methodology. We selected 19 data sets from the UC Irvine repository, and we chose 1 or more classes to be anomalies and the rest to be our nominals. And then we manipulated 4 properties of the data set that we thought might be important for these anomaly detection algorithms. One is the relative frequency of the anomalies. Are the anomalies extremely rare, like only 1 in 1,000 of the points is anomaly, or are they very common, say 10% of the data points are anomalies? We vary the point difficulty, which is a measure of how much the anomalies overlap the nominals. We added irrelevant dimensions to see if that would confuse the methods. And we tried to look at whether points were tightly clustered or not. And the idea here is that density estimation methods, you might have a cluster of anomalies, and a density estimation method might assign that a high probability and therefore not detect those anomalies. So we end up with about 11,000 non-trivial benchmark data sets, so a huge amount of data. And then we evaluated actually 9 different algorithms, because we also threw in the k nearest neighbor simple distance-based method. But we had 2 density estimation methods, 2 quantile methods, 3 neighbor-based methods, and 2 projection-based methods. And then we did an analysis of variance in which we tried over these 10,000 data sets to ask how well can we predict a metric as a function of the relative frequency, the point difficulty, the clusteredness, the irrelevant features, the mother data set, which would be to say the parent data set, the data set from of the 19 data sets, the one that was used to generate this, and finally, which anomaly detection algorithm we're using. Because as you have no doubt discovered, which algorithm is best for your problem varies from one problem to another. And that turns out to be true here, that the choice of this mother data set is the single most important property of a problem that determines how well you'll do. And then the second most important typically was the algorithm, or else the relative frequency of the data points. But we wanted to do this analysis to assess the effect of the algorithm choice while controlling for all these other factors. And our metric was the area under the ROC curve for the question, is this a nominal point or an anomaly point? So here are our results, the mean AUC effect. So this is the, and what we found was that the method that was the most effective was actually the k nearest neighbor method. And then in second place was the isolation forest. And then there's like a 3-way tie for third place using 2 density estimation methods and LOF, which is another nearest neighbor method. And quite to our surprise, this was a sort of a baseline method that just computes the distance to the mean. So the distance to the mean of the nominal data. And then this was the one-class support vector machine and support vector data description. Those 2 quantile methods perform very poorly in our benchmarking. And we still don't really understand why. But part of it, I think, is that we are interested, when you measure area under the ROC curve, you're measuring a ranking loss, right? You want to know how well can the method rank the anomalies over the nominals. And those methods are not good at ranking because they just create a decision boundary rather than creating a score. Okay, well, I wanted to end. I'm going to have to skip my computer vision slides, but I'll just end with a discussion of some applications of these techniques to cybersecurity and fraud detection. So, as I have mentioned, in most applications, anomaly detection has a significant false alarm rate. And this means that in general, you need a human in the loop. When you get an anomaly alarm, the human needs to examine that alarm and decide whether it's a true alarm or a false alarm. But given that you're going to have the human in the loop, we should be able to exploit that, because now we're getting a source of feedback. We're getting labels on our alarms. And so in research that was done by Shubhamoy Das and Amran Siddiqui, 2 of our graduate students, and Alan Fern and myself, we looked at introducing feedback into and exploiting it. So the idea is we've got our data, and we assume we're getting a batch of data, say a whole day's worth of cyber security information or a whole month's worth of financial transactions. We fit an anomaly detector to that data and then score the training data itself. This is particularly easy to do with the isolation forest. And then we find the data point that has the highest anomaly score and present it to the analyst. And then the analyst has to say, no, this is a false alarm, or yes, this looks like a true alarm. I'll have to create a trouble ticket or launch a fraud investigation or whatever. And so then we want to feed that back to the anomaly detector. And we published a couple of papers, particularly at KDD 2018. And what we found is that incorporating analyst feedback yields huge improvements in anomaly discovery. So we like to plot things this way, that on the x-axis here is the number of candidate alarms that we have shown to the expert, to the analyst, and the y-axis is the number of those that were true alarms. And so this black curve here is what we get if we don't have any feedback from the analyst. We just present our alarms in descending order of anomaly score. And you can see that after 100 alarms, we have discovered about 22 true positives. So we have about an 80% false alarm rate. Now, Shubhamoy Das and Wenqin Wang and the rest of us had this paper on what we call active anomaly detection, and we're able to boost that up above 50% true alarms. And then with this method called GLAD OMD, which is online mirror descent, we're able to get up to 70% true alarms. So you can see that you go from only 20% true alarms to 70%. This is just a huge win. Now, I was a little worried about this because this was done on benchmark data sets, and we know that the anomalies there come from well-defined classes for which the features are adequate because it's been designed for classification. Well, we were part of a grant in which there was a red team that was introducing advanced persistent threats, so cyber attacks, into a small computer network that had 3 hosts on it. And so in the sort of same style, we would we extracted features from network flows, from operating system calls, and processes, and then put those feature vectors through random forest or isolation forest anomaly detector. And now what we're plotting on the vertical axis is the number of false alarms before we get a true alarm, where we detect the fault, right? Detect the intrusion. And these are with error bars. And so we can see that this is the baseline without any feedback. It takes on host number 1 about 42 false alarms before we get a true one, whereas with analyst feedback, it only took 3. And on host 2, it was similar. It took us about 11, I think, to detect the problem instead of 62 or whatever. Host 3, we only cut it down by a factor of 2, but still you can see there's a huge win here in incorporating analyst feedback. Well, how did we do it? What we did was you can transform an isolation forest into a gigantic linear model. For every node of these isolation trees, it becomes a Boolean feature. And when you have a query and you drop it through the tree, each node that it visits turns that feature on. So most of the features will be zeros, but except for the ones along the path from the root down to a leaf node that this particular query visited. And in each tree we'll get that path. Now, we're going to assign, those are going to define our features, and then we're going to define weights, and initially the weights will all be set to 1. And the idea is that if we multiply those weights times those features, we're getting the sums of the isolation depths of all of the data points. So it's the non-normalized isolation depth of XQ. But then we can adjust those weights. So the idea is that based on analyst feedback, we're going to tune these weights. And we applied these modern online convex optimization algorithms like online mirror descent to do this. And I'm just amazed at how efficiently, how rapidly online mirror descent learns. And you can see the payoff in those curves. Okay, well, I will stop here. So I don't have time, unfortunately, to do computer vision work, but that I have. And let's see if I can see summary. So I described general anomaly detection methods. I spent most of the time on density estimation because this is the area that has been most deeply studied. And we talked about parametric distributions like fitting a single Gaussian, fitting a mixture of Gaussians, kernel density estimation where we put a little tiny Gaussian in every data point, noise-contrastive estimation where we convert the problem into a supervised learning problem by basically generating simulated anomalies, uniformly randomly sampling in a space, and then flow models, which use deep neural networks. And then I briefly described the quantile methods, distance-based methods, and the projection methods, and described this application to cybersecurity and fraud detection. I didn't have time to talk about anomaly detection and computer vision. Things are very confusing there. We do not really have good methods yet for computer vision. Probably the most successful things are to introduce auxiliary tasks to a neural network that are self-supervised and use the performance on a self-supervised task. If it's poor, then it suggests you shouldn't trust the main task. Okay, well, I have the last thing I want to emphasize is anomaly detection is important. It's critical for building robust AI systems if we want to apply artificial intelligence in safety critical, high stakes applications. And of course, there are many, many practical applications as well. But it is difficult. Our methods are moderately mature for tabular data sets with meaningful features. Fundamentally, the methods rely on some notion of distance, but anomaly detection is very challenging for images where we need some notion of semantic distance. And it's not clear that our deep learning methods right now are learning good hidden representations that have a good distance in them. So research right now is rapidly advancing. There's plenty of room for PhD and master's dissertations because we need better methods and we need better theoretical understanding. Okay, well, let me stop now and answer questions. I have my references here for your enjoyment later. So are there questions I can answer? Please put them in the chat. I realize this is a very technical presentation compared to yesterday.
They're probably just writing it out. They were following with their laptops and their notepads, so they are having they need a break to write it in the chat box. So if you have any questions,
I'll just wait for a little bit here. Yeah. So the question is, could anomaly detection be used for car crash detection? So you're thinking about trying to prevent a car crash, or maybe if we were looking at say we had mobility data from cell phone data, we could build a model of the expected traffic density. In Lagos, it's just always high, I guess. But we could build a model of of the probability distribution or density estimation for how dense we think the traffic will be on each street in the city each hour, say, or each 15-minute period of time. And then if there was some kind of a traffic jam, a crash, or something else, a blockage of the road, then that would show up as an anomaly, because if normally traffic was flowing okay, it would be an anomaly. Also, the reverse could be true. If normally there's a lot of traffic in a place and suddenly there isn't any, that would show up as an anomaly as well. Yeah, in fact, I don't know if people like whether traffic police are actually using this kind of thing. but that's something you could look at. It's certainly used a lot in data centers where you're trying to do load balancing across multiple machines. And if you see that you build models of the typical loads on your machines as a function of the mix of customers, and if you see a problem that might be the result of a potentially failing disk drive or a processor that's having troubles, then you can raise an alarm and see if you can migrate the workload off of that machine and take it down. Let's see. In using isolation forest, which performs well, can the data set be used for building a model? And is it accepted theoretically? Right. So at BigML, the number one use that we have for anomaly detection is for data set cleaning. But your question, I think, is very important, which is there's a risk when you clean the data that you're removing that you're not removing errors, you're actually moving signal, the important things. And this is especially true if you have a very heterogeneous population, say of users of some kind. You might be filtering out a small subpopulation of users that could be very important to your business because you're treating them as anomalies. And so this is another reason that you really need to be able to drill down. You get an anomaly score for every data point, but then you really need to look at that data point and ideally understand where it came from, who collected it, and have a theory about why it is a bad data point, not just rejecting it because it has a big anomaly score. Let's see. How important is negative sampling in machine learning? I'm not sure what you mean by negative sampling here. This would be if you have a highly imbalanced set where you have a lot of negative data, or is it about this noise-contrastive technique? I'll move on. Ogunaran, you can answer my question and I'll look at the next one. In fraud detection bank transactions, how does the different approach pick out possible fraudulent transactions? And the key features are usually transaction amount, time, and so on. Right, so I didn't talk at all about designing good features. I think that that's quite challenging. I worked on a problem that was looking for people who might be stealing information from an organization, and so-called insider threat detection. And there, we had features about each user each day as they were using their computers, like number of websites visited, number of programs executed, things like this, number of files copied. They were intended to get at whether they were copying data and sending it off-site to some other computer system. And we found it very useful to normalize each customer or each user by what their own typical behavior was. So you could calculate basically a histogram of their typical behavior, and then, like, someday, so you might say that the number of times, for instance, that a secretary might execute the sudo command to do some administrative thing might be very low. Whereas if it's a system administrator, they might be doing it all the time, right? And so the anomaly you're trying to detect is when the secretary starts behaving like a system administrator. That means that that the secretary's computer may have been compromised, right? So what we would do is take each user's number of websites visited and ask, well, on a typical, oops, we're almost out of time. And a typical day, what would be the quantile of this day compared to a typical day? And we would replace the number by the quantile and then put that into our anomaly detection systems. So that was normalizing each user by their own behavior. We also did it organization-wide because every day, if some interesting article was shared throughout your whole organization, everybody might go visit a new website, but that doesn't mean that, that the system is under attack. Okay, well, thank you very much for your attention and your comments, and I guess we have to go now. So I will see you again. Connect
Okay,
with you
guys.
on LinkedIn.
Thank you so much, Professor Thomas. Please make sure you're appreciating him in the chat. Connect with him on LinkedIn and Twitter. I'm dropping the contact again so you can keep up the conversation.
Okay, great. Thank you.